Good afternoon. We're going to walk through what we were doing at the end of last week. I think that's how long ago it was. Anyway, we're going to look at function pairs that are inverses of each other, in which one is exponential and one is logarithmic. And we're going to do all the details therein that you saw in class. So let me make up an exponential function here. We could say y equals, well, let's do something similar to what we had as an example in class. I don't remember exactly how it went, but it was something like this. Oh, something like that. And then maybe, tell you what, maybe we'll add something to that. Well, I'm thinking about this for too long, really. I hate to have just all these. Anyway, there you go. Basic example. So what do we want to know about this? We want to know the intercepts, and we want to know the domain and range, and we want to know the asymptotes, right? And we also want to know all these things about the inverse function, the inverse of this. And as we know, there's symmetry here with the original function and its inverse. So whatever this thing is, we also want to know all these things. And instead of just answering all this and then transferring it over, it's usually easier to start with knowing both function equations and then going from there. So let's figure that out. What do we have as this equation? Okay, so it's the inverse of this. So we can start by switching x and y, right? So here's how I start. And now I just have to get y by itself. So this is already the inverse, right? I've already got it in a sense. The relation is, the domain and ranges have switched places. So now I just got to get y by itself, and I'm going to do that with a log. But first I have to get this part right here by itself. So I'm going to subtract 6 from both sides, and I'm going to divide by 2. Now this part that I boxed in, here we are. This part that I boxed in here is isolated, so we're ready to write our log equation. So we can say log what makes the 3 into this guy, the result here, and the answer is the exponent 5y. And then we can divide by 5 on both sides. And dividing by 5 is the same thing as, we'll put a 1/5 there. So I'll write it up here. So we'll say y equals 1/5 log base 3 of this. Okay? So I just noted the 1/5 multiplying by a fifth is the same as dividing by 5. So that just allows me to keep it on one nice line. But other than that, there's no difference in writing it in the two different ways. Okay. So what I have been showing you guys is the y-intercept is handy as a starting point because we know how to get that pretty quickly. All we have to do is substitute 0. So if I plug 0 in here, I have 3 to the power of 0. That's 1. 1 times 2, and then plus 6, that's going to give me 8. So I know my y-intercept. Now I can come over here and do the same thing. So if I put 0 in there for x, I have negative 6 over 2 is negative 3. Then I've got log base 3 of negative 3, and that doesn't exist. There is no log base 3 of negative 3 because I can't take a number, raise it to a power. I can't take positive 3 and raise it to any power and get negative 3. It can't be done. So therefore, there is no y-intercept. And then we can use symmetry to say, well, if this has no y-intercept, then by definition of an inverse, or just by symmetry of an inverse, if that's got none of these, then this cannot have any x-intercepts. And if this has the one y-intercept at 0, 8, then by symmetry this one must have the one x-intercept at 8, 0. Right? So I can use these to you know, to figure out. Of course, I could also get the x-intercept by substituting 0 for y and then solving and whatever, but you know, essentially I've already solved it. I've already done the algebra to get both inverses, so I don't need to do it again. Okay, now I just want to point out, suppose this, see that's a -6. Suppose that had been a +6, and I'll change it back, but suppose that had been a +6. Well, then there would be a y-intercept. As a matter of fact, it'd be a rational number, because look, if I take 0 now, if I put 0 in for x, look what I have. That'd be +6/2, that's +3. So what makes 3 into +3? Well, 1. This log would be 1, and I'd have a fifth times 1, and then I'd have a y-intercept here at 0, 1/5, and then I'd have an x-intercept there at 1/5, 0. So that would, all that would happen. So you might see something happen like that, but you know, just to warn you. Okay, so we're done with that. Now domain. We'll look at the two domains first. Okay, now you notice we were not able to put 0. We have no y-intercept. We couldn't put 0 in there for x, which means that the domain is going to exclude 0. As a matter of fact, I also can't put +1 in there, because +1 minus 6/2, that's also a negative number, and the argument would still be negative, even with that x equal to +1. So would +2 work? No, same problem. So how great does x have to be before we finally have a safe value? Well, even +6 won't do it. If I substitute +6 in there, 6 minus 6/2, that 0, log base 3 of 0, still doesn't exist. However, +6 is the boundary. So you can see this for yourself, you know, in the calculator or whatever, but it's logical. 6 is the lower bound of the domain. So I'm going to write that. X is greater than 6 for the domain. 6 is the lower bound of the domain. X can be anything greater than 6, but it can't be 6, or this would be 0, and it can't be less than 6, or x would be, sorry, if x is equal to 6, then the argument would be 0. And if x is less than 6, then the argument would be a negative number, right? So if we graph this thing, we'll see that. As a matter of fact, why don't we graph it? So let me just, let me pause the recording for a second. Okay, so you can see I've loaded in both of the functions here, and this one right here in particular, I have to do something kind of long to put it in. So I've got 1/5 in parentheses times log. Now this is the log of the argument. Notice the x minus 6 has to happen first, and then it gets divided by 2. So I have x minus 6 in parentheses divided by 2, and that expression itself is in parentheses as the argument of the log. And then I divide that by the log of 3, because it's base 3. So I had to take all those things into consideration when I entered this into the calculator. So let's look at the graph. Okay, so that's going to be the exponential, right? And it's still thinking. Okay, and I can barely see the log. I'm going to pause it while I get the window maybe to look better here. Hold on. Okay, so actually, I'm having trouble getting it to look any better than this to show both functions at the same time on the TI screen. You'd have to, if you really wanted to see the behavior of the function on this screen, you'd have to adjust the window to look at them separately. And here, you just see a little bit of a curve, and it's just so steep and so sudden that the resolution can't handle it. Fortunately, we don't really need the calculator to do this on the test. And I'll show you, I hesitate to do this, but I'll show you what it looks like on Desmos. That's the exponential, and that's the logarithmic. And we don't, that's just to satisfy your curiosity, but you can't use Desmos on the test. So, but nevertheless, let's talk about, let's just imagine what that shape looks like. We know that the domain is going to be where x is greater than 6. So it's 6 from here on out is the domain, and we can't use any of this. It's only out here. Okay, so what's the domain, just to continue on, what's the domain for the exponential function over here? Okay, so here, and we've said this many times in class, but it would be all real numbers because there's just no reason why a particular number would not be able to be used as our x value. I mean, all we're doing is taking 3 and raising it to a power, and the expression of that power is just our exponent, and the expression of that exponent is just 5x. So there's just nothing stopping us. I mean, you can try whatever you like in the calculator. You'll always get a defined result. So all reals is the domain in general for our exponential function, unless there's something really weird which you won't see. And then for our log functions in general, we're going to have a boundary, and usually it'll be a lower bound, but we could put a negative on this thing and make it an upper bound. Actually, the negative would be here on the variable inside. But this is just, you know, with a bound, so it's got a lower bound. So the ranges are just going to be a reflection of what we see in the domain. The domain and range switch places. So if this domain is all real numbers, that means in this inverse function, of course, I can get anything as a result. The range would be the same as the domain here. And so if I'm only allowed to input values greater than 6, then the only thing I could possibly get out of this function are y values greater than 6. All right. So now these asymptotes here, and we can start by saying, well, if this domain has a lower bound of 6, that means that that's the vertical asymptote of that function. So we saw sort of the graph of that. I mean, it's doing something like this, right? And it's stopping here. It's not really, I don't know if you can say that it's stopping, but it's, as we get closer to 6, this value goes to negative infinity. We can't get to 6 itself, and we can't get beyond it to the left, right? So since that is the lower bound, that's where the asymptote is, right? So we could say our vertical asymptote is x equals, x equals 6. And do we have a vertical asymptote here? We can say no, we don't, right? So notice, the vertical asymptote and the domain, they're always connected. In this sense, right, the only way to have a vertical asymptote is to have a value that's not in the domain. 6 is not in the domain here. That's an opportunity for one of these to exist. Everything's in the domain here. That means there is no opportunity for this to exist. So these are always connected. All right, and then of course, horizontal asymptote reflects this vertical asymptote. So I've got this right here, which means I'm going to have a horizontal asymptote at 6, which the exponential function is going to asymptote down to that horizontal line. Okay, and then the horizontal asymptote, no, there isn't one, because that reflects here as well. Okay, we're going to do one more example here, and I'll go a little faster this time. So let me see. I'm going to make it up. I'm going to say we have, here's my bottom line here. I don't want to draw below that. Okay. So this time let's start with a log function. So let's start with a log function that actually has a y-intercept for a change. So let's say we have y equals 2 log of x plus, I don't know, 10. Minus 1. Okay, so we'll start by getting the inverse. So I'll do that down here. I'll say I've got x equals 2 log y plus 10, because, you know, in the end we're going to get the same information here. That's the goal, of course. So I'll add 1 to both sides. I'll divide by 2 on both sides. I don't mind you doing those steps, you know, all at once, because you're experts at those kinds of steps by now. And then, oh, we didn't use a base. Okay, let's make the base, I don't know, 10. Why not? So I can do 10 to the power of this horrible thing equals y plus 10. So then I just subtract 10 on both sides. So I've got y equals 10 to the x plus 1 over 2 minus 10. All right. All right, let's do all this stuff. So we've got x-intercepts and y-intercepts, and I'm always just suggesting that the y-intercept is easier. It's easier for most people, but you could also start by finding the x-intercepts and then reflecting those, or whatever, or you could find both of these and reflect them, or whatever you like. So I could plug in 0 here. I wind up with 0 plus 1 over 2. That's a half. That's 10 to the 1/2. Well, that's a square root of 10. That's 3 point something minus 10. So I'm going to get like negative 6 point something. So I got to, you know, ask the calculator. That's the square root of 10. Negative 6.83, so negative 6.84. So we'll do 0, negative 6.84. And then here, oh, look, it's going to be nice. I don't need the calculator. I can put 0 in. 0 plus 10 is 10. Log base 10 of 10, that's 1. 1 times 2 minus 1, that's 1. This crosses at 1. So I can get my x-intercepts here, which will just be reflections over the identity function. Okay, domain. Maybe you're not shocked to learn it will be all real numbers. Again, all I'm doing is raising a number to an exponent and subtracting a number. There's nothing that's not going to work here. Okay, here I can see 0 works, right? So what doesn't work? Well, negative 10 wouldn't work because that makes a 0 argument. Negative 11 wouldn't work because that makes a negative argument. So negative 10 is the boundary, see? Anything greater than negative 10, I could have negative 9. I could have negative 9.999. Any of that would make a positive argument, and I'd have a value, a defined value as my output. So I can say x must be greater than negative 10. Not strictly greater, not including negative 10. Okay, range. The ranges reflect the domains. Asymptotes. Vertical asymptote's easier for me because it connects right to the domain. Right? So you could say domain, the boundary, the lower bound of the domain is negative 10. That's where the vertical asymptote is. Domain is all real numbers, no vertical asymptote. All right, there you are.